physics. Today we're going to be looking at a new term. Well, it's a term you've heard many, many times in your life, but perhaps not in a physics concept or in a context, and that term is work. So going back to our analogy where we compared energy to money, work would be like either putting money into a system or taking money out of a system. And so work is going to be considered positive if energy enters the system, or it's going to be negative if energy leaves the system. And typically this is referring to kinetic energy. Okay, so we have a couple of different ways of looking at energy, or looking at work done. So one of the formulas that we have for work done in its most basic form is just the change in energy. So this is one way of looking at it. It's how much has the energy changed in a system due to some outside force. But this isn't very hard to calculate. We're going to give you one more formula for work done, which is this. It's going to be force times distance, and this part here is cos theta. We're going to multiply that by cos theta. Now I want to give you just a couple of examples to help you kind of figure out what the meaning of this cos theta part is. So if we think about, I'm going to draw three different scenarios here. So what is, we've got a block, or let's call this an ice skater. So we've got an ice skater sitting on a block. Now this ice skater is just sitting on a giant slab of ice, and I'm going to come along and push the ice skater. So I'm applying a force this way for the ice skater. So force is going to be our red arrows. And that object, or this ice skater, is going to move to the right. And so our distance is going to be this green colored arrow here. Now in this case here, what is the angle between these two arrows? Well, in this case, the angle is going to be 0 degrees. And so if we want to calculate the work done, it's going to be whatever the force is, it could be 2 newtons, 3 newtons, whatever, multiplied by the distance, multiplied by cos of 0 degrees. Now, some of you may know this already, but let's calculate here. What is cos of 0 degrees for you? Well, cos of 0 degrees is 1. So in fact, what this is saying is, if you are pushing an object in one direction, and the object is also moving in the same direction, then our formula just simplifies to being F times D. So that's if it's moving directly, directly to the right. Now what happens if now the object is going to be moving, well, let's undo that here. I don't know why I moved down there. Okay, so in this case here, what happens if the object is moving to the right, but I apply a force to the left? So an example of that is, the ice skater is now moving along, and it's carrying along, and it's moving to the right, and all of a sudden I apply a force to the left to slow it down. Well, first of all, let's ask ourselves, what is the angle between these two vectors? So the force is to the left, the distance is to the right, and so theta is going to equal 180 degrees. This means that we're going to have force times distance times cos of 180 degrees. And what is cos of 180 degrees? Well, you may know this already, but if not, let's see. It is -1. So in this case here, the work, when you're going in opposite directions, is going to be equivalent to negative force times distance. In other words, you're taking kinetic energy out of the system. It was moving to the right, so it had some energy, and now I've applied a force to the left, so I've taken away that energy from it. Okay, let's try one more time to draw this diagram, but instead of having the force going to the right, let's have the force going straight down. So let's say someone comes along and jumps on their shoulders and they're pushing straight down. So we've got this extra force moving down on the ice skater as they move to the right. We're still assuming it's completely frictionless. So there's no friction on this ice. If no one is pushing it to the left or right, it's not going to speed up or slow down. Well, what is the angle between these two forces? We've got this extra force vector going down. We've got the displacement vector. It's moving to the right. Well, the angle here is going to be 90 degrees. And so if our work is force times distance times cos 90, I'm sure many of you have kind of clued in already to what this is going to be, but let's see. Cos 90 is 0. So in other words, the work done equals 0 when the two vectors, the force vector and the distance vector or displacement vector, are perpendicular to each other. So hopefully this makes sense. If I'm on a skateboard, for example, I'm going to be pushing down on the skateboard, as I'm standing on it, I'm pushing down on it. But if it's a completely frictionless skateboard, if there's absolutely no friction whatsoever, well, that skateboard's not going to slow down just because I'm standing on it. It's going to keep going forever and ever and ever because it's frictionless. So if you're applying a force perpendicular to the direction of motion, it does not give the object more or take away any energy from the system. It's still going to have the exact same amount. The work is going to be 0 if the force and the distance are perpendicular. Okay, let's try a few sample problems. So, example number 1. If I were to lift a 30 kilogram weight up off the ground to a height of 1.5 meters, how much work would be done on the weight? So let's take a look. Here is our weight initially, and we're going to lift it up. So at the end, it's going to be at this position here. So here's our initial, here's our final down here. We know the mass is 30 kilograms, and we know the height here is going to be 1.5 meters. So this is our height, or the distance that we're moving. Now we know that work done is going to equal force times distance. Well, let's assume for a moment that we're lifting this up at a constant velocity. That would mean that we have the force of gravity going downwards, and we've got the force that we applied here, and if it's a constant velocity, those two will be balanced. So the force that we're applying upwards is going to be equal to the force of gravity, which means it's going to be equal to m times g. That's our force of gravity. And we're going to move it a certain distance, but that distance that we're moving it is this height. So instead of using the letter D, I'm going to use the letter H, because hopefully you're seeing some alarm bells here that this seems very, very familiar. So in other words, the work done is just the m times g times h. Now, the reason why you're recognizing this is because we've done this for the last 2 weeks. This is our formula for potential energy. So the work done, though, is, again, tying it to this formula up here. We said it's the change in energy. It's going to be our final energy minus our initial energy. So work equals, it's going to be the final potential energy minus the initial potential energy, and this is going to be m times g times 1.5 minus m times g times 0. So because the distance we lifted it, the d that we traveled, is this height, is 1.5 meters, this is just going to simplify. This, again, is going to cancel out. We'll just be left with essentially mgh. So whenever we're lifting an object against gravity, this formula is always going to be the same. So work is going to be the change in potential energy, which is going to be m times g times, I'm going to be a bit more specific and say delta h, because it's not just how high it is, it's telling us how far it's moved, or the change in the height. So work is going to be m times g times delta h. So this is the work done against gravity. So whenever it's lifted against gravity, m times g times delta h is going to be our work. mgh would be our energy at a specific point. Work would be our change in energy, which means it's going to be m times g times delta h. Okay, and one more example here for us. We have got a pineapple, and that pineapple is, let's draw this pineapple out here, and this pineapple is being lifted, or sorry, it's being held stationary 1.2 meters above the ground. So this is up here, and we have 1.2 meters, and it's being held there for 15 seconds. So how much work is being done on the pineapple? Well, many of you may have already figured out the answer immediately. If not, take a minute, pause the video, and see if you can figure this out for yourself. Okay, if you haven't figured it out already, or if you have, we can just go through the answer and confirm what you already know. In this case here, the work done is going to be the mg times delta H. Now, what is delta H in this scenario? Well, it started at 1.2 meters and it finished at 1.2 meters, so the delta H is going to be 0. So what that tells us is that when an object is just being held stationary, there is no work being done. So no displacement means no work done. Now, if you're confused, because obviously you've all held objects at some point in your life, and you may be thinking, okay, but if I hold a pineapple for a long time, my arm's going to get tired. Why is that if there's no work being done? And that gets a little bit complicated, but one way of thinking about it is that your muscles, your individual muscle fibers, they do have to continue to work. They don't just pull and stay stationary. Each of your muscles is each of your little muscle fibers is taking turns. So they're all kind of taking turns pulling individually for a brief moment in time. It's kind of this sort of spastic motion. So as they continue to individually squeeze, those individual muscles are doing work. They're applying a force. The muscles are contracting when they do that. And so that will mean that you are expending energy. So for a human holding something, yes, you will use energy to hold an object, but that's just because your individual muscle fibers are all doing a little bit of work. If you rest something on a table, for example, well, you don't need to replace the batteries on your table. That table will be just fine to sit there indefinitely holding any object you want for as long as you want, provided it doesn't break the table, and there is no energy being done there. It's just stationary. There's no individual muscle fibers, anything like that. So in this case here, the work done is 0. And I don't think I actually answered this question here, but we can answer it now. So again, we're going to have, for this question here, just to quickly reroute us back here, it's going to be 30.0 times 9.8 times 1.5, and that is going to be 30 times 9.8 times 1.5. That gives us 441 joules. So actually it should be 440 joules, 2 sig figs. That is going to be our answer for how much work would be done to lift a 30 kilogram weight 1.5 meters. Okay, let's look at a couple more examples here. So number 1, we've got you are pushing a 10 kilogram pumpkin horizontally 5 meters at a constant velocity across a level or horizontal surface with a force of 3 newtons. So here's my pumpkin here, and here we go, add a little stem to it. So here's my pumpkin here, and I'm applying a force of 3 newtons in this direction here. So let's use a red arrow. So this is 3.0 newtons. That's the force I'm applying, and it's moving a total distance of 5.00 meters. And so you'll notice that maybe you noticed that I was very careful with how I worded this question. Because what I said is, how much work did you do when you are pushing the pumpkin? So in other words, what we're looking at is just this force here. This is the force that you have applied. This is your applied force, which is 3.00 newtons, and you are moving at 5 meters. Now there are other forces involved here. So one of those forces is going to be the force of gravity. This would be, well, 9.8 times 10, so this would be 98 newtons down. There's going to be the normal force, and that's going to be 98 newtons upwards. And because we're moving it at a constant velocity here, that also means that this force to the left is also going to be 3 newtons, because it's going to be equal to this force here, just like these two forces are equal. So when I ask you how much work did you do on the pumpkin, well, first of all, pause the video and do a quick calculation and solve it, and when you come back, we'll discuss it. Okay, if you're back, Fairly straightforward calculation. You probably didn't need to pause for that long. Work is going to be force times distance times cos theta. Again, you don't really need to worry too much about the cos theta if you think about the fact that it's going to move to the right and you're applying a force to the right. And if you're both going in the same direction, this just becomes 1. So it's just going to be force times distance. Again, that's 3.00 newtons times 0.00 meters, which is going to be 15.0 joules. That is how much work that you did. Now, there's other forces in play here. So there's the force of friction, for example. How much force did the force of friction, or how much work did the force of friction do? Well, two ways of looking at this. One, if you want to look at the work done by friction, you can say that again, if the force is in one direction, which is going to be to the left, and the distance is in another direction to the right, then you can just realize that's going to be negative if they're in opposite directions. But you can also just rely on this formula to keep you honest. It's still going to work this way. So in this case, the force of friction is 3.00 newtons, the distance is 5.00 meters, and the angle is 180 degrees, because one's to the right, one's to the left. And in this case, this is going to give us negative 15.0 joules. So you'll notice that you gave the pumpkin 15 joules of energy, and friction took away from the pumpkin 15 joules of energy. So if I ask you how much work did you do, well then that's going to be the force that you applied. If I were to ask you how much work overall was done on the pumpkin, we can see that the answer would be 0. And this should make sense because work is saying it's a change in energy. So from where the pumpkin started to where the pumpkin finished, did it gain potential energy? Well, no, it's still on the same level surface. From where it started to where it finished, did it gain kinetic energy? Well, again, that's no, because it was moving at a constant velocity. So it didn't gain potential energy, didn't gain kinetic energy, and so the change in energy for the pumpkin is going to be 0. So when you're looking at the total work done, it's going to be 0. There's no change in energy. When you're looking at the work done by you, it would be plus 15, and the work done by friction would be negative 15. Okay, let's try one more question here. And please, I'm going to draw the video, but please pause the video after the drawing is done. And I want you to try and calculate on your own how much work did you do to the box. And the force that you applied is a pulling force or a tension force. So I'm going to quickly draw this out for us, and I'll get you to try and answer this on your own. So this is the 50 kilogram banana box. It's being pulled 11 meters in this direction. You are applying a force of 90 newtons, 90.0 newtons, and that is an angle of 35 degrees from the floor. There are other forces here. There's gravity, there's normal force, and there's the force of friction. But we don't care about any of those forces for now, because right now we're just wondering about the work that you did from your pulling force. So we're just worried about the work done by tension. So pause the video now and try giving this question a chance. All right, if you are back, hopefully you have tried this. Otherwise, you're missing an opportunity to learn. So please make sure that you are pausing the video when I suggest to do so, and trying the problems for yourself. So I'm going to solve this two ways. So one of them is just using this formula that we've been using from the beginning. So this one is force times distance times cos theta. In this case here, the force is 90 newtons, the distance is 11 meters, and the angle is 35 degrees. And if we do this calculation here, so we have 90 times 11 times cos 35, that's going to give us 811 joules. Yeah, 811 joules. So that is how much work you did, or how much energy you added to the box. Now I want you to think about this problem in another way. So one way of looking at it is just using this formula. It's easy, you can trust it, it works, that's fine. But I also want you to be able to think about it this other way here. So when we have this force here. So this is our force of tension, 90 newtons. Just like we were doing before with forces, we can break them into components. I'm going to call this Ft in the x direction and Ft in the y direction. And this is 35 degrees. So Ft in the x direction is really the one we're concerned about. And the reason why I say that is because we do work when we have a force or a component of force that's in the same direction as the motion. So the force is, the x component of the force is in the x direction, straight to the right, and the distance itself, the displacement, was also in this direction here. So we can kind of ignore the effect of the y component because it's not acting in the same direction as the displacement. So in this case here, what we want to figure out is the work is the, we're just going to try this a second way here. So it's going to be the force in the x direction multiplied by the displacement in the x direction. So what we're concerned about is the two components of this that are facing are in the exact same direction as before. So if I want to solve for fx, I have to take a little detour here. So I know if I'm using, this is the adjacent side and the hypotenuse, so we have cos of 35 degrees equals ftx over ft, and that means that ft in the x direction is going to be ft times cos 35. Okay, and now the distance in the x direction is just the distance, which is 11 meters. So let's put this as a formula. So we're going to use the f in the x direction, which is ft times cos 35, and we're going to multiply that by the distance, which is 11, or just we can call it distance for now, and then we'll plug in the numbers. So this is going to be 90 newtons times cos 35 times 11 meters. Well, let's take a look at this, 90 times cos 35 times 11, and compare it to this, 90 times 11 times cos 35. And hopefully you'll see, it doesn't matter order of operations for multiplication, this and this are the same thing. We can easily rearrange this 90 times cos 35 times 11, we can rearrange those by flipping them around, and we'll have the exact same answer here. So again, this is going to be 811 joules. So when you're using this type of formula here, you can either use force times distance times cos theta, or you can just use the component of the force in the direction of displacement. And then again, if it's in the opposite direction, then that's going to mean negative work. So if we're pushing in the same direction it's moving, it's going to get faster and faster, gain kinetic energy. If we're pushing in the opposite direction to where it's moving, it's going to get slower and slower, and it's going to lose that kinetic energy. Okay, hopefully everyone's with me so far. So let's take a look at a familiar problem, but we're going to add a little bit of complexity to it to do with work done. So we've solved problems like this where we have an object that's on a ramp like so. So this is my object here on the ramp, and it has, I forgot to add a mass, so I'm just going to say m equals 50 kilograms. So that's the mass of this object. The height of the object is 1.5 meters, and we know this is 25 degrees, and it has an initial velocity of 2.5 meters per second. Now, in this case here, it's more complicated because there's this external force. So we have an external force. Now, if we had solved this, what we were doing last week, we weren't dealing with friction. So this would have been an easy question. We would have solved this by the same method. So the sum of the initial energy is going to be the sum of the final energy. In this case here, we had the potential energy initial because it's at the top of a ramp. We had the initial kinetic energy because it's moving at 2.5 meters per second. And then the final energy would just be kinetic. So that would be how we would solve that problem. And we were all quite confident in doing that. But now we've got this external force. And this external force is friction. And we're going to take a look at normal force briefly. You'll see that it's not an important force in this case here. But there is this external force of friction, which is going to be either adding or taking away some energy from the system. So in this case here, if we zoom in, the displacement of this object is going to be in this direction here. So this is our displacement, and we can solve for that displacement. We can solve this value here because we know the angle and we know this height. So if we want to solve this, it's going to be adjacent over hypotenuse. So sine of 25 degrees equals 1.5 over the distance here. And so the distance is going to be 1.5 divided by sine 25, which is going to be, let's see, 1.5 divided by sine 25 is going to give us 3.55 meters. Okay, so that's this displacement here, 3.55 meters. That's how far it's going to go down the ramp. So the displacement is in this direction, but the force of friction is going to be going up the ramp, and that's going to be this 16.9. So F equals 16.9 newtons in this upward direction, opposite to the displacement. So please answer the following two questions for me, and then we'll go on to the third one together. So what is the work done by friction on the block? That's the first question here. The second question is, what is the work done by the normal force? So again, this is our normal force, and I'm worried about the work done by the normal force. So solve these two questions, and once you have, restart the video, but pause it for now. Okay, if you're just coming back, let's try and solve this problem here. So, work equals force times distance times cos theta. Now, we know our force is going to be 16.9 newtons. That's our force of friction. We know our displacement is going to be 3.55 meters. And we also know that the angle between the displacement down the ramp and the friction up the ramp is going to be 180 degrees. So if we solve this, we're going to have 16.9 times this 3.55 answer times cos of 180. And that's going to give us negative, let's call it negative 60 joules. So to two sig figs, yeah, negative 60 joules. That is the work done by friction. It makes sense that it's negative for two reasons. One, the displacement and the force are in opposite directions. And secondly, we know that friction is going to slow something down. It's taking away energy. It would be going faster. It would have more kinetic energy if it wasn't for the sake of this friction, which is removing from it. Number two, let's take a look at this one here. So work done by the normal force is going to be the normal force multiplied by the displacement and multiplied by cos of the angle. Well, the normal force here is, well, who cares? Let's call it 10 newtons. And you'll see why I'm being so cavalier with this. The distance here is 3.55 meters, and the angle here is 90 degrees. So the displacement is parallel, the normal force is perpendicular, and so we're going to get cos 90. And hopefully you remember what cos 90 is. Well, cos 90 is a big fat zero. And so, what is the work done by the normal force? It's also going to be zero. Again, just a reminder, when force is perpendicular to distance, work equals zero. So there's no work done if the normal force and the displacement are perpendicular to each other. Okay, so this is not changing the system. And now we're going to go back and solve this similar to what we did last week, except we have to add one more bit of information in here. So, same way we answered before. The initial energy and the final energy are listed like this, but now we have to think about what are all of the bits of external forces which are causing some work to be done, or some gain or loss of energy. So we had this before. The initial energy was, what forms did we have? We had initial potential energy. We also had some initial kinetic energy, and that was it for our energies. And then we had our work done, and this was the work due to friction. And this is going to equal our final energy, which is just our final kinetic energy. In this case here, this is going to be mgh plus 1/2 mv initial squared plus work due to friction, and I might as well just, I'll leave it as that. Work due to friction. We already solved that one up above us. That's going to equal to 1/2 mv final squared. And now we can solve for this here. So 50 times 9.8. Oh, you know what? Sorry, I should have gotten you to pause the video here. Hopefully you did. If not, pause the video here, solve it for yourself, see what answer you come up with. My apologies. I forgot to remind you. Okay, hopefully you have tried it on your own. Let's try this together though. We have m times g times the height plus 1/2 times 50 times the initial speed squared, which was 2.5 meters per second, plus negative 60 equals 1/2 times 50 times v final squared. So this is going to be 49 times 1.5, which is 49 times, let's just do that, 9.8 times 50, oh, it should be 490, oops, times 1.5. This is going to be 735 plus 0.5 times 50 times 2.5 squared. That's going to be 156.25. That's right. Minus 60 equals, we'll just say 1/2 50 is 25 times v squared. Okay, so let's add this all together. 735 plus 156.25 minus the 60. So that's 831.25 equals 25 v squared. I'm going to divide both sides by 25. And that means that I have 33.25 equals v squared. And take the square root of that. We're almost done here, folks. And that's going to give us final velocity, v final equals, how many sig figs we got here? 2 sig figs. So v final equals 5.8 meters per second. Okay. This one here might help you with this week's quiz. Hint, hint. Okay. The block is now sliding on the ground. So we know we're continuing from here. So it's moving at 5.8 meters per second. In this direction here. That's what my block is doing. And we have some friction along here, and the friction is applying a force of 18.6 newtons. There's these two forces here as well, Fg and Fn, but they're going to cancel out, plus they're perpendicular to the direction of motion. So this is the direction of motion here. They're perpendicular, so we know they're not going to do any work, because the gravity and the normal force are both 90 degrees to the direction of motion. So the only force that's going to have an impact on it is going to be this force of friction. There's no forward force anymore, just this momentum carrying it through. And so let's see if we can solve this here on your own. Please pause the video and come back when you've got the answer. Okay, I'm sure you've all paused it and solved it, and here you are. So it's moving at 5.8 meters per second squared. So you could solve this using kinematics. You know the force and you know the mass, so therefore you can find the acceleration. And you could use acceleration, and then you could do this whole part up here. d v naught v a t. You could solve acceleration. It's going to be this force divided by 50. Solve the acceleration. You know the initial v naught is 5.8. V is going to be 0. And you can solve for it. That's fine. We want to try something new here. So let's try something new. We know the kinetic energy. So we are going to look at this to start with here. So the sum of the initial energy plus the work done equals the sum of the final energy. Well, this object's coming to a stop. It hasn't gained height. So the final energy, there's no kinetic and there's no potential. The final energy here is going to be 0. So the initial energy that it had, again, there's no potential here, just the kinetic. So this is going to be 1/2 mv squared, our kinetic energy, plus the work done. Now I'm going to change work done to its formula, which is force times distance, and times cos of 180. which I'm just going to leave as -1. Sorry, it's messy. So I'll just leave it as cos 180. We can do the calculations the next time around, because we know it's moving to the right, the force is to the left. And that's going to equal 0. Okay, so we'll carry on from there. So we've got 1/2 times 50, so we have 25 times 5.8 squared, plus 18.6 times distance times -1 equals 0. And so that's the same as saying minus 18.6. I'm just moving the negative sign. So let's see. I'm going to square this. I'm going to multiply that by 25, the 1/2 times 50. So that's going to be 831.25. I think we already had that before. 831.25 is 1/2 mv squared. So we had that before, and that's going to equal our force times distance, or our work done. So this is going to equal 18.6 times the distance. And so let's divide this by 18.6, divide both sides by 18.6, and the distance is going to be 45 meters. So in this case here, the kinetic energy that we had up here, so this is equal to, again, this is equal to just 1/2 times 50 times v squared. I just simplified it to 25 v squared. So the kinetic energy is going to equal the work done, because we know the kinetic energy plus the work done means that it comes to a stop, means that the final energy is 0. So this is an easier way, in my opinion, of doing these kinematics. You figure out what that initial energy is, and that's just going to be force times distance. So the energy equals force times distance gives us the answer of 45 meters. That's how long it would take to come to a stop. Okay, that's it for the week. I know it's a bit of a longer video. My apologies for that. There are 11 questions here. Please don't feel obligated to do all 11. That's a lot of work. Do as many as you feel you have time for. This is not sorry, not the marked assignment for the week. The marked assignment for the week is going to be the quiz that you complete. So that's the one that will be for marks. It's going to be marked easily, or it's going to be marked, I guess generously is a good term to put it, but these questions are always going to help you prepare for that quiz. So do as many as you feel you need to. The answers are also on the bottom. And I hope you found this to be a worthwhile and educational lesson. Thanks.